How are you all doing today?
Good, how are you?
Doing well. There were some questions that were asked via email regarding a homework problem for homework set 8 and a problem on one of the practice exams as well. So I'm going to work through those before we jump into what we were supposed to get to today. So homework 8 problem 4 says that a certain practical current source provides some amount of power, and it's out to like 12 digits or something insane, to a particular load with a fixed resistance. And that same practical current source provides some other amount of power to another load. So let's start with what a practical current source is. Does anybody remember what that is from lecture 8?
Yes, sir. It's a current source in parallel with a resistor.
Okay, that's absolutely correct. So it's not a K. Got ahead of myself there. So we have this situation. There is a current source, IS, in parallel with a resistance RS, and this is what's forming our practical current source. Connected to our practical current source are a few different load resistor values. So we could determine this voltage drop, VL, the voltage drop over our load resistance, or we could determine our current, IL, the current flowing through our particular load resistance. Because this is a practical current source, I'm going to be working with that quantity, IL. So, let's see, I can use voltage division and find that IL will be equal to IS multiplied by 1 divided by RL over 1 divided by RS plus 1 divided by RL, which is the same as IS multiplied by RS over RS plus RL. So from this, power absorbed by my load resistor is going to be IL squared times RL, because power in a resistor is I squared times R. So that's going to give me IS squared. Let's see. RS squared RL divided by RS plus RL quantity squared, if I've done my algebra here correctly. And I believe that I have. I squared the numerator of my fraction, I squared the denominator of my fraction, I remembered to square IS, and I multiplied it through by RL. So this relationship is an important one in this problem. And actually, let me go ahead just to make it super clear. this is equal to the power absorbed by our load resistor. So the reason why this guy is important is because we have two different values for PL, and we have two different values for RL. And we also have two unknowns, IS and RS. So we can actually develop a system of equations, two equations with two unknowns, using our given values of PL and RL, and use them to solve for IS and RS. Now, parts A through B of this problem are presupposing that you have figured out what IS and RS are, like what their values are. So hopefully it's clear how you can use this equation that I've boxed in orange to find those values. Again, if you have two different values of PL and a corresponding value of RL for each of them, you can set up a simple system of equations, two unknowns, solve, 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 and you'll figure out what IS and RS are. So moving forward, part A asks you to determine the value of RL, VL, and IL. So we want RL, VL, and IL when VL multiplied by IL is at its maximum. Can anybody interpret what that question's really asking? Let's start there. So what does it mean when VL multiplied by IL is at its maximum?
The maximum power?
That's exactly right. So this is asking you this question, part A specifically, is asking what the value of RL, VL, and IL will be when maximum power transfer occurs. Well, we know that maximum power transfer occurs when RL is equal to RS. By definition, I think in my pre-recorded lecture, I derived it for a practical voltage source. And then when we had our in-class meeting on lecture 8, I think Jesse Munoz asked me effectively to derive the maximum power transfer relationship for a practical current source. So we should have that as well, but I'll write it up here. Pmax is 1/4 IS, dang it. IS squared times RS. Okay. So under the assumption that RL is equal to RS, what value would VL have? So in our circuit diagram up at the top of the screen, if RS and RL are equal, how would I solve for VL?
Well, the current would just split evenly, so it'd be 1/2 IS times RS.
Okay. That is perfectly acceptable. So 1/2 IS, because that's the amount of current that's going to flow through either of our two identical resistors, multiplied by RS gives us the voltage drop. So that's perfectly acceptable. Alrighty, and then you've actually already answered this question, but what value should IL have when RL is exactly equal to RS?
One half IS.
Yeah, 1/2 IS. So nothing wild or crazy there. Part B asks for you to determine RL, VL, and IL when VL is maximum. So looking back, sorry, my dog is starting to bark. He's getting unruly. Looking back at our schematic diagram, what value of RL will cause VL to be its largest possible value?
If all the current flows through it, so if RS is shorted,
So if RL is a short circuit, then VL would be the voltage drop over a short circuit, which would be 0. So when RL is a short circuit, that is the condition that
oh,
is required for IL to be at its maximum.
sorry, so it'd be an open circuit then.
Right. So
Sorry.
if RL is an open circuit, then VL will be at its maximum value because none of the current will split. All of it will flow through that resistor RS. And we can see that VL would be the voltage drop over resistor RS as well. So RL would be an open circuit, which we would represent as infinity. In web work, you can just type in the letters INF, and it will interpret that as infinity. What would be the value of VL under the condition that RL is an open circuit?
IS times RS.
That's exactly right. Oh, and IS was a capital. And finally, what will be the value of IL?
0.
0. All right, our last case, part C, asks for us to determine RL, VL, and IL when IL is at its maximum. So we've already discussed this a moment ago, but for the current to be at its maximum value requires our load resistance to be a short circuit or 0 ohms. So what value will VL have when RL is 0? So if this RL resistor here on the right-hand side is a short circuit, then VL represents the voltage drop over short circuit, which must be what?
0.
0 volts. What will the value of IL be if RL is a short circuit?
IS.
Yeah, all of the current will flow through the short. None of it will branch off and flow through our resistor. And that is problem 8, homework problem, dang it, homework 8, problem 4. So it's just taking what we know about power transfer and applying it to a practical current source. Any further questions on homework 8 or any homework problem actually? All right, well, I was also asked about a particular problem from one of the practice tests, so give me a moment to see what that is. Let's see, fall practice exam number 15. All right, so that is a resistor combination problem, and the person asked me effectively how I redrew it. So let's get a new piece of paper here. All right, and just so that I'm looking at my original and not the solution. All right, so we have a rather ugly looking, so let's see, this is fall problem 15. Rather ugly looking resistive network. We are asked to find the resistance between terminals C and D under the constraint that the value R is 11 ohms. So what I'm going to do is I'm going to identify all of my nodes. And I'm going to label them. So this green node is obviously going to be C because it's connected to terminal C. This blue node will be D. So I'm going to call this guy up here A, B, there's C, D, here's E, F, and G. Now what I did in my solution to this problem, I may not have done that in this class, and I'm not sure why, because I actually like to do it. But what I effectively do is connect the dots and just use resistors to find the points of interconnection. So let me explain what I mean by that. So what I would do, so I would start with C on one side of the page and D on another side of the page, and then figure out effectively how many different pathways I can go to make this happen. So for instance, between C and D directly, there is an 18 ohm resistor. So I would put an 18 ohm resistor here in the middle, like so. Now let's look at that top path. To get, well, let's see here. So from C to A, I have a resistor R. Let's call this point A. From A to B, I have a 20 ohm resistor. And from B to C, I have a 14 ohm resistor. So what does this mean for this particular branching path?
It's a short.
Yeah, it's all shorted out, so none of those guys actually matter. So if I go the bottom path, I'm going to go from, let's see, this is an R. All right. So I'm going to erase these guys because I didn't give myself really enough room here. But all those guys got shorted out, so they're not going to contribute anything anyway. That's not what I wanted to do. All right, so we're looking at the bottom paths now. So from C to G, there is a resistor R. So I'm going to put G here. Looks like as good a spot as any. And from G to D, oops, there was a 9 ohm resistor. And now I have my path from C to E. Where we had an 8 ohm resistor. From E to F, we have a 6 ohm resistor. And from F to G, we have a resistor R. And so let's see. I have that 8 ohm resistor, 18 ohm resistor taken care of. I have the 9 ohm resistor between D and G taken care of. I have the resistor R between C and G taken care of. I have the 8 ohm resistor between C and E taken care of. The 6 ohm between E and F taken care of. And the R between F and G taken care of. All right, so from here, it should be fairly straightforward to see how to simplify this thing. You would combine the 8, the 6, and the R in series, place them in parallel with R. That combination would be in series with the 9 ohm resistor, and that combination would be in parallel with the 18 ohm resistor.
What
So-
was R again?
11 ohms.
Okay, thanks.
So let's see if we can figure out how to do this mathematically. Let's see, in one equation it might be kind of ugly. So we could call R bottom 8 ohms plus 6 ohms plus R, where R is equal to 11 ohms. R bottom is in parallel with this R. So we would have 18 ohms in parallel with R in parallel with R bottom. In series with 9 ohms. And then do the math from there. So that's just really an alternate way to redraw resistor networks where, again, I'm just connecting different node points with resistors. I find it useful. You guys may or may not, whatever floats your boat at this point. We've been combining resistors all the way through the Engineering 120 series and now through the first few weeks of Engineering 221. So whatever method you're comfortable with works for me. Any other questions?
Can you scroll back down?
Certainly.
Okay, thank you.
All right, well, then let's jump into our in-class assignment. So why is this larger than it needs to be? Today we are going to be doing Thevenin and Norton equivalent circuits that contain dependent sources. So this first problem tells us that we want to determine the Thevenin voltage as seen by the load resistor RL of the circuit above. And we are going to assume that the positive polarity for the Thevenin voltage is on top. So let's see, I have 12-volt source, 6.3 kilo ohm resistor. Since I'm finding the Thevenin voltage with respect to the resistor RL, that means I take it out of the circuit. So there's an open circuit terminal where the resistor RL was, and those open circuit terminals are what's going to give me my Thevenin voltage. I have my dependent source plus minus 0.5 Vx. Let's see, I have a 2.8 kilo ohm resistor. I have a current source that is 2 milliamps. I have a 1.1 K resistor over which the voltage Vx is defined. 1.1 kilo ohms plus Vx. Alrighty. Any thoughts on how we would approach determining what that Thevenin voltage is in this case?
Nodal analysis, maybe?
Nodal analysis. All right. What should I choose as my reference node?
The bottom one, because
The
it's
bottom.
connecting the most.
Sure. So there's my reference node. So I'm going to have a voltage here, VA, voltage here, VB, and a voltage here, VC. Technically, I guess I have another one. We could call it VD over here. But we know that VD is equal to 12 volts, so that's why I wouldn't really even bother assigning it an actual nodal voltage. Our other voltage relationship would be VC is equal to 0.5 Vx. What's Vx going to be in terms of our nodal voltages?
VB over 1.1 kilo ohms.
So VB divided by 1.1 kilo ohms is the current flowing down through the 1.1 kilo ohm resistor.
Why not just be VB?
That's exactly right. So it's the voltage, the nodal voltage associated with the positive polarity terminal, which is VB, minus the nodal voltage associated with the negative polarity terminal, which is ground or zero. So VB minus 0 is equal to Vx.
Yeah, that was my fault. Sorry, I misheard the question.
No problem. So VB is equal to Vx. So that means VC is equal to 1/2 VB. All right, so the only place we'll actually need to apply Kirchhoff's current law then is at node B. So that's going to be VB minus VA over 2.8 kilo ohms minus 2 milliamps plus VB divided by 1.1 kilo ohms is equal to 0. Solve these guys, which means I need to go find a calculator real quick. it appears I've left all three of my calculators at my office on campus. So can somebody help me out here and set up this system and solve it?
I can, sir.
Okay. So
Which equations would be used in the system? Would it be the KVL, VB, and then VB equals VX?
So let's see. We have three unknowns, right? So we'd definitely be using this guy. We'd definitely be using this guy. Am I missing an equation? I am. I'm missing an equation. That's the issue. All right. So the equation that I'm missing, I'll sneak it in here, is I didn't do KCL at node A, and node A isn't a supernode, so I should have done it there. So that would be VA minus 12 divided by 6.3 kiloohms plus VA minus VB over 2.8 kiloohms is equal to 0. So there's equation 3. Sorry about that. Has anyone managed to set up and solve this system of equations?
Almost done. Give me 1 second.
Let's see. No.
Okay. I haven't double checked it yet, but for VA, I got 5.95 volts.
Okay.
And for VB, I got 3.256 volts. I may need to double check it though. So
Nope, those are right. I'm looking at I found my solution to this that I had already done a couple of quarters ago.
Okay.
What did you get for VC? That's an important one.
let's see.
So it's just going to be 1/2 of whatever you got for VB.
1.625.
All right.
Yeah, that's what I got.
1.5. All righty. So how can I use these nodal voltages to get the Thevenin voltage? So what's the nodal voltage associated with the positive polarity terminal of the Thevenin voltage?
Would it be
VA.
VA minus VC.
VA minus VC. Yep, because VC is the voltage associated
dang
with
it.
negative polarity. So 5.95 minus 1.625 What's that going to be? So let's see, 5.9 minus 1.6 looks like 4.3. My mental math, there's some rounding error in there, but that's close
That's-
enough for this guy.
That's exactly what I got. Okay.
All right, so I feel confident that we were able to solve for the Thevenin voltage. This one was maybe a little bit tricky. All right, so our Norton current. What do we do with the resistor RL?
You short it out.
Short it out, exactly right. And then we find the current through the short. It's going to take too long to look that route. So, how do you guys feel we should figure out what that short circuit current is? Like what circuit analysis technique?
Could we technically still use nodal? Oh, my bad.
Very good. I mean, the super node.
So somebody asked if we could technically still use nodal analysis. And the answer to that is yes. So do you want to use nodal analysis and give it a whirl?
Which one, in your opinion, would be easier, mesh or nodal? That's kind of what's confusing me.
All right, so let's think about this. And that's a good question of when to use nodal versus when to use mesh. So in this case, there are, and I'm just going to do these in, I'll do them all in orange. So here's one node, two nodes, three nodes, four nodes. One of them will be reference, which means we're going to have a system of equations, three equations, three unknowns. Or we would have one mesh, two mesh, three meshes, which means we're going to have three equations, three unknowns. So the level of difficulty of the system that we're going to have to set up is effectively the same. So then that begs the question, we're trying to find a current, and if we do KVL, all we're going to find is our nodal voltages, which means we're going to have to establish one more relationship at the end in order to figure out what I Norton is. Or if we use mesh analysis, we can just use a simple current relationship to figure it out. And so what I mean by that is if we used KVL, where my mind goes is we would have to use our nodal voltages to determine this current, our nodal voltages to determine this current, and then add these two currents together and they would give us I Norton, right?
Yes, sir.
Applying Kirchhoff's current law at that node where all these things are separated. If we did nodal analysis, mesh analysis, we would take this current minus this current, and it would give us I Norton. So in this case, it really doesn't matter which approach we use because we're effectively going to have to do the same number of steps. So neither one is more efficient than the other.
So just to switch it up a little bit, can we actually do mesh analysis with this one?
Sure. So I'm going to
I
call
still
this,
need practice with it.
Yep, no problem. I'm going to call this mesh A. This will be mesh B. And so this guy will be mesh C. So we have an interior current source. So we are going to have a current relationship equation. So what's that going to be?
INO is equal to IA minus IB.
Okay, so that's not the one I was looking for, but that's definitely
my bad.
what we're going to have to do, so no problem there. So I Norton is equal to IA minus IB. How are we going to express the current flowing through the current source in terms of our mesh currents?
2 milliamps is equal to IC minus IB.
Alrighty. So IC minus IB, because as IC is going around its clockwise path, it's flowing up through the branch that has the current source, which is in the same direction as the arrow of the current source. And it's minus IB because IB is flowing down through that branch. All right. So let's write our super mesh equation around this loop. Starting at the bottom left-hand corner, right here, please. Somebody go.
Negative 0.5 Vx.
Yeah, you see the negative sign first, and it's a voltage source. So yeah, negative 0.5 Vx. What's next?
Plus 2.8 kilo ohms times IB.
All right, and what is next?
Plus 1.1 kilo ohms times IC. Equal to 0.
Equal to 0. Great. Now let's get an equation for mesh A. Starting at the bottom left-hand corner and working our way clockwise around mesh A's loop.
Negative 12 volts
All right.
plus IA times 6.3 kilo ohms.
All right.
Plus 0.5 Vx is equal to 0.
Okay. So we have three equations, but we have a fourth unknown here because we have Vx. So how are we going to express Vx in terms of our mesh currents?
Uh, 1.1 kilo ohms times IC.
Exactly right. So we have a total of four equations, four unknowns, but we could substitute this guy into here. And that's the wrong thing. I really need to have more than one mouse for two computers here. It's driving me nuts to switch back and forth. All right. So my results for this, I got IA was 1.759 milliamps. IB was negative 0.328 milliamps. And IC was 1.672 milliamps. Let me make sure. Yeah, I wanted. Okay. So we can now use this guy and find that I Norton is 1.759 milliamps minus negative 0.328 milliamps, which means I Norton is 2.087 milliamps. I'll give you guys a minute to punch all those equations into your calculator and confirm.
Yep, that's what I got.
I got as well.
Same here.
Cool deal. Well then, now that we know this part is correct and our Norton current was correct, how would we go about finding R Thevenin in this case?
The Thevenin voltage divided by Norton current.
Right. So for any problem that contains a dependent source, so if it contains independent and dependent sources, it's probably easiest to simply take the ratio of the Thevenin voltage divided by the Norton current to determine the Thevenin resistance. So 4.319 divided by 2.087 milliamps equals 2.069 kiloohms here. Nothing wild or crazy there. Just using the relationship again. RTH is equal to VTH by I Norton. Maximum power, since we know I Norton and V Thevenin, P max will just be V. I don't know why I keep wanting to put my subscripts as superscripts today. V Thevenin squared over 4 R Thevenin, which will be identical to 1/4 I Norton squared times R Thevenin. That's just our maximum power transfer equations applied to a practical voltage source that is our Thevenin equivalent circuit on the left-hand side, or a practical current source that is a Norton equivalent circuit, which is this guy on the right-hand side. So all of our maximum power transfer equations still work.
Where did the 1/4 come from?
So when, all right, let me scroll here. Oh, there's not a lot of it. Okay. So if we have a practical voltage source, V Thevenin in series, some Thevenin resistance, and then that is in series with the Thevenin resistance as well, because we want maximum power transfer to occur. Our load voltage here, VL, is just VTH divided by 2. Our power absorbed by our load is VL squared divided by RL. So that's going to be, oh my gosh, VTH over 2 squared times 1 over, in this case, our load resistance is V Thevenin. So when we square that denominator, that's where that factor of 4 comes from.
Okay, I see. So basically it's like you already plugged in Ohm's law into the VTH over 2.
Yes.
Okay, that makes
And,
sense.
The 1/4 comes in the current one comes from the fact that the current is going to divide evenly. So I Norton divided by 2 is going to flow through the load resistor. And then when you square that, you get I Norton squared divided by 4 multiplied by your load resistance, which is RTH.
Okay, that makes sense.
Alrighty, any other questions on this first problem? Alrighty, let's jump ahead to this guy. So we're asked to use a test source method to determine the Thevenin resistance as seen between the terminals A and B of the circuit. So the test source method means that we can apply either a voltage source or a current source. It's our pick that has a particular magnitude that is, again, entirely up to us. So what would you guys suggest we do here?
A voltage source.
A voltage source, okay? Anybody else okay with a voltage source? So to be clear here, either of them will work, but in some cases, one may be easier than the other. So let's start with a voltage source. Do you want positive polarity on top or bottom?
On top.
All right. And what value of voltage do you want to use?
1 volt.
1 volt. Okay. So our goal then is to figure out what this current is, I test, because R Thevenin will be V test, which is 1 volt, divided by whatever I test is. So how would you go about solving for I test now?
Wouldn't you use mesh analysis?
We can use
Or-
mesh, certainly. So let's call this guy mesh 1, and this guy mesh 2. Okay, so there are no current sources at all, so we don't have to worry about super meshes or anything like that. So somebody tell me what my Kirchhoff's voltage law equation for mesh 1 is going to be, starting at the bottom left-hand corner.
Minus
Negative
1 volt.
1.
All right, negative 1 volts. What's next?
Plus 1.6 kilo ohms times I1.
What's next?
And plus 8.4 kilo ohms times I1 minus I2. Equal to 0.
Is equal to 0. Okay, I'm good with all that. All right, who wants to do my Kirchhoff's voltage law equation around mesh 2? Starting from here and going clockwise.
I2 minus I1 times 8.4 kilo ohms.
2 minus I1, okay.
Plus I2 times 7.5 kilo ohms.
All right,
Plus 2Vx is equal to 0.
okay. So we have 2 equations and 3 unknowns. So somebody else tell me how I'm going to express Vx in terms of my mesh currents.
Vx is equal to 1.6 kilo ohms times I1.
That works for me. So we have 3 equations, 3 unknowns. So we should be able to solve pretty easily. So I1, I2, X, let's see. All right, so somebody else give me the results, because this is not the way that I happen to do it, and we'll talk about that in a moment when I made my solutions guide out for this.
All right, I think I got it.
What you got?
I1 is equal to 0.1378 milliamps.
All right,
I2 is equal to 0.045 milliamps.
all right.
And
Yeah.
then Vx is equal to 212 over 961.
All right, well, VX isn't really important to us. So if we know what I1 is, I test is exactly equal to I1 based on our circuit diagram, correct?
Correct.
So what
sir.
is V test, which is 1, divided by I test, which is 0.1378 milliamps?
I got 7.256 ohms.
0.256.
Oh, wait, hold on. I forgot it's milliamps. 1 second.
So if you're dividing by milliamps, that's going to give you kilo ohms.
Kilo.
So a little bit of rounding error, not a big deal there. So that is a perfectly sufficient way to solve that problem. Now let's talk about a slightly different way to solve the problem. I don't know if it's any better or worse or anything. I'll just give you a hint into how I think, I guess. So let's erase some of this stuff. So I used mesh, but I chose to use a current source. I used a 1 amp current source. And so my goal was to find this test voltage. So let me explain why I used a 1 amp current source. We don't have to bother going through the whole problem again. But the reason why I chose a 1 amp current source was because I would know exactly how much current flows through this 1.6 kilo ohm resistors, which gives Vx a fixed value. In this case, 1600 volts. So I probably should have chose a 1 milliamp source, but it is what it is. It doesn't particularly matter. So once I know what Vx has to be, I no longer have to worry about having dependent sources or anything like that. So to me, it just made the problem a little bit easier. I did still have to come up, since I wanted the test voltage, which is the potential difference between here and here, what I did was I added Vx plus this voltage drop over the 8.4 kilo ohm resistor, which is easy to determine using currents, mesh currents I1 and I2. So a different way of going about it. You could also have chosen to do nodal analysis instead of mesh analysis. There's no wrong way to work these problems. Just do whatever you're comfortable with. But typically speaking, when I look at a problem like this, where I'm applying a test source method, I usually see if I can effectively figure out what the controlling variable is, so Vx, Ix, or whatever. Like I choose a test source that will let me effectively define what that controlling variable is, just to, in my opinion, make the math a little easier. But you don't have to do that. We just did this problem without it, and it was pretty straightforward. So, all right, any further questions on Thevenin and Norton equivalent circuits or anything else right now?
I'm good, sir.
All righty, so tomorrow is going to be a review session. So let me explain how that's going to work. I'm going to show up at 10 or whatever on Zoom here, and then you guys are going to say, hey, Dr. Hartman, could you explain how you got the answer to some particular test problem or a homework problem or something like that, and then we will work it. When you guys stop asking me questions, I'm gonna leave and go work on your test. So the meeting could be 5 minutes or it could be 2 hours. It just depends on how much you guys are willing to put into it. So just wanted to give you a heads up. All right. So unless anybody has anything else, I will catch you guys tomorrow at 10 a.m.
I have a quick question. What time is the exam on Thursday?
6 p.m.
Okay. And you said it was 35 questions?
That is correct. So it will be the exact same format as the practice exams that I have put online. So 10 questions at the beginning that if they require a calculation, it's what I would call a back of the envelope calculation. So real simple, might be a few definitions and things like that, like definition of voltage or current or power or energy. And most of that stuff should be available in the notes. And then after that will be 25 questions that are actually going to involve like doing math and stuff. And I don't know if any of you guys have noticed, but on the exams, I typically do like the problems that I put on there follow the same order of the order of material that we covered. So I start off with stuff from lecture 1 where it might be power and energy relationships or current charge relationships and stuff like that. Then move on to having to use KVL and KCL. Then from there, superposition. From there, nodal and mesh. And from finally, there will be source transformation problems. And then at the very end, I guess I do deviate technically. I give what I call a big ugly nodal and a big ugly mesh problem, where you don't actually have to solve anything. You just need to identify the correct equations, which that is the exact same thing as I've done in the practice exams that I've given you. So if you don't know what I'm talking about, go look at the practice tests.
And one more question. How are the points like distributed from each problem? Is it like based on the difficulty of them, or?
No, it's 3 points per problem.
Okay. All right.
There's a total of 105 points. Your grade is out of 100. So there are 5 bonus points built into the exam.
Okay.
So if we've taken circuits before, if we've taken those exams, we can expect the same style, same everything.
Yep, I've been the jerk that's been making out the circuits test for, I guess it'll be 3 years at this point. So if you've taken one before, then you should reasonably know what to expect. I'm not reusing any old tests or anything like that, so it'll be all new problems. But yeah, same level of jerkness, I guess.
Dr. Hartman,
Yes.
are we using Lockdown browser for the exam?
Yes.
Okay, thank you.
Yep. So as I have mentioned previously, we will be using the Respondus lockdown browser for this exam. It will require access to your webcam and all that kind of good stuff. I'm expecting you to, like write down your work and all that kind of good stuff. And then I am going to create a place for you to upload all of your work, say within half an hour to an hour of when the exam closes, so that I can be sure that you're the person working the problems, etc. So just find some scratch paper and then take pictures of it or scan it or however you've been submitting your in-class assignments, do that. Any other questions?
So on our scratch work for the exam, are we going to put our answers on there, or are we going to put them on a Scantron?
So the test is on Moodle, and so it'll be multiple choice on Moodle. So you will be able to select the answer that you get.
Okay, thank you.
So it's not going to be a Scantron or anything like that. It's literally going to be just, so A is 0.6 volts. If that's the correct one, you check the box for A and then move along to the next one. Let's see what's going on in chat here. Test will be out of what lessons? Okay, so the last time it did not include Theven and Norton. This time it will also not include Theven and Norton. So the exam is covering lectures 1 through 8. That being said, Thevenin and Norton equivalent circuits could be a way for you to solve problems as well. There's nothing, I'm not going to stop you from using it, but I'm not going to require you to use it on this test. There will be a total of, I believe, 5 Thevenin and Norton problems on exam 2. So I will, I'll expect you to retain what we've covered these last couple of days and then use that for exam 2, whenever the heck I decided to give that one.
So basically all the way to source transformation?
Up to and including source transformation. That is correct.
Okay.
And maximum power transfer theorem, which was part of the source transformation lecture.
Will we not have class on the day of the exam?
That is correct. You will just show up and take the test. We're having the review session tomorrow, so Thursday. Spend your day, I don't know, studying or fishing or whatever you do to get a clear head and take an exam.
All right, thank you.
Are you still available for office hours this week?
Yes. Just shoot me an email and we can set up a Zoom meeting if you want to go that way, or if you want to just correspond by email, that's fine by me too. I'm not going anywhere. Any other questions?
No, sir.
All righty. Well, I'll catch you guys tomorrow morning then. Have a good rest of your afternoon.
You too. Thank you, Dr. Harmon.